Hello class, in this video I'm going to show you how you can perform a chi-square goodness of fit test. So let's go ahead and read this problem. So first of all, it says suppose any new movie being made has the following expected star rating distribution as follows. So the number of stars, 5 stars, 4, 3, 2, 1, are then the ratings. This is then has 5 categories, and then the expected percentage of stars for each new movie is 15% for 5 stars, 24% for 4, 33%, 17%, and 11% for 3, 2, and 1. So this is then going to, when we see something like this is then the distribution of one categorical variable. So if we're going to do some sort of hypothesis test, then we can't do a general chi-square test because we only have one categorical variable, so we'll do a goodness of fit test. After a new movie debuts, a sample of 500 moviegoers were then asked to rate this movie. The table below will summarize then the results of their ratings. So the number of stars, 5, 4, 3, 2, and 1, and then the observed counts for each individual who voted for or rated the movie as 5, 4, 3, 2, or 1 star. So 85 said that the movie was 5 stars, 125 said 4 stars, 162 said 3 stars, and 75 and 53 said 2 and 1 stars. So this is then our observed count, what we actually saw from a sample of 500 individuals. So is there evidence then that the new movie has a different star rating distribution than we would expect it to, given this percentage above? And we should use then a significance level of 0.10. If we do this type of procedure, we should do a chi-square goodness of fit test because we're basically just then testing whether or not this one categorical distribution is this. Or if there's evidence that it's different from that. So the null hypothesis for a goodness of fit test is that each proportion is equal to some value. In this case, we have that the proportion of 5 stars ratings should be 0.15 or 15%. The proportion of 4-star ratings should be about 24% or 0.24. The proportion of 3-star ratings should be 0.33. And the proportion of 2-star ratings should be 0.17, and the proportion of 1-star ratings should be 0.11 or 11%. So this is then the distribution that our null distribution that we should expect to see, and the alternative hypothesis is that just one of these proportions is different from what we would expect it to. So the next step in doing the chi-square goodness of fit test is that we should calculate the expected counts. And how can we find these values? Well, essentially we have a sample of 500. We can either know that our sample is 500 from here, or we can just add up our observed counts to get our sample size. And then we multiply the 500, or the number of observed counts, times then the expected percentages. So 0.15 times 500 should give us 75. 0.24 times 500 will give us 120. 500 times 0.33 should give us 165, and so on. And so that's how we can find our expected counts. Just multiply the sample size times the expected percentage for each category. Now let's go ahead and calculate our chi-square test statistic. We can do this a couple of different ways. We can either calculate it by hand by using the general formula. So for a chi-square test statistic, whether we're doing a general chi-square test or the goodness of fit test, will always be the observed minus expected counts divided by the expected counts, all squared, and then add all of those up for each cell. So in this case, I have shown the calculation for this, and we should expect to get a chi-square test statistic of 2.845 with the degrees of freedom of 4 and a p-value of about 0.58401. So if we don't want to do this by hand, we can also use our TI-84, and this is how we'll do it. Go ahead and get out your TI-84, turn it on, and the first thing you should do is go to the lists. So recall that goes to Stat, and you want to click Edit, and in your first list you want to put in the observed counts. So this was this column up here, observed counts. So in order we have 85, 125, 162, 75, and 53. And so once we put in our observed counts, we should put in our expected counts in the second list. So then 75 is the expected count for 5 stars, 120 is the expected count for 4 stars, 165 is the expected count for 3, and then 85 and 55 are the last expected counts. Okay, so basically what we're going to now be testing is how far or how different are these, and if they are different, are they significantly different? So now we can then calculate the chi-square test statistic by going to Stat, scroll over to Tests, and keep scrolling down until you get to the chi-square GOF test, Goodness of Fit test. Some of you guys won't have this on your calculator, and that's okay. You can always be able to calculate the chi-square test statistic using this formula, and I won't expect you to be able to find the p-value either on the exam or on this activity. So everything you see on this activity is basically what you'll be expected of on the exams. So go ahead and click the Goodness of Fit test. Then we have L1 is our observed counts, that's what we put in. L2 is our expected counts. And then lastly, we have degrees of freedom of 4 because we have 5 categories. Minus 1 is a degrees of freedom of 4. And then we should press calculate. And sure enough, we get a chi-square test statistic of 2.845, a p-value of 0.58 with degrees of freedom of 4. All right, so that's how we can use the TI-84 to get our chi-square test statistic and p-value. So the last thing we should do is state our conclusion. So suppose our p-value from this test then was 0.5841. Let's go ahead and state our conclusion in the terms of the problem. So how we can do that? Well, it looks like there's no evidence that the distribution of star rating is different than what we have claimed. We then fail to reject the null hypothesis at a significance level of 0.10. Why? Because we have a really pretty large p-value and there's just no evidence from the expected ratings or from the observed ratings and the expected ratings that they're any really different. So this movie seems to be rated as expected. Hopefully this video helped you understand how to do a chi-square goodness of fit test.